Everyone, welcome to the video lecture of structural geology, and I'm going to start the first chapter of structural geology while discussing the deformation, because most of the structural structures that we study in structural geology are as a result of deformation, whatever they are: fold, faults, joints. Most of them are result of deformations. Okay, so we have to understand deformation first before proceeding to the further chapters in the structural geology. First of all, try to understand deformation with the help of this definition. Deformation is the transformation from an initial to a final geometry by means of rigid body translation, rigid body rotation, distortion, and we can in simple language call it strain, and or volume change. That means you can only say a body got deformed if you can see any rigid body translation, rigid body rotation, any distortion in shape, and or any volume change in the body. In a simplified version, we can actually classify this kind of deformation and we can represent them as shown in this flowchart. So this deformation can be of any basically four type: rigid body translation, that means the body is not changing its shape, rather it is being translated from a position to another position. Then it is distortion, strain. It can be further divided into pure shear and the simple shear. Then we have rigid body rotation. Here the body is rotated in its own axis, and we might have volume change. So these are representation of different kind of deformation that a body may go under deformation. We can call it body deformation if it show any of them or a combination of them. Okay, so let's discuss about each of the kind of deformation one by one. First, I am going to talk about rigid body rotation. As we can see here, the object which is in the light color, this is square and it is rotated. So this point comes to this point, this point is now becomes this point, and similarly all the point, it is simply being rotated. No change in the shape, no change in the volume has taken place. So this is the rigid body rotation. So when a body do not show any volume change, any shape change, and just rotate in its axis, we call such deformation as rigid body rotation. And these vectors are showing displacement field, and these vectors are showing the path of these particles. Okay, and how this can be made is represented in this diagram. So this point is migrated to this point, okay, while rotating, and this the rotating axis must be at this center position, and it will be perpendicular to the screen. Okay, and the example of such rigid body rotation, although here I have shown example of a garnet which is being rotating, although it is not a rigid body rotation, as we can see a bit of deformation in the shape also. uh, so we can't say it is a proper rigid body rotation, but it is an example of rotation. So we know that rotation uh, is a deformation which is possible in rock. So you don't have to be in a fluid medium to rotate a particle. Okay, so rotation can also be achieved in a solid state rock. We do study the flow of the particle of or the flow of the grain in the in the rigid body or in the solid body, and it is come into the topic rheology, and we will discuss it later in the later chapters. Okay, but for now we can take the example of granite. This is the rock, some metamorphic rock. uh, it appears to be nice, Okay, and in this gneiss we have this garnet. Okay, and when we see this garnet in plane polarized light in petrography, when we do the petrography and look at this garnet in plane polarized light, we can see the garnet, this fleshy color garnet, and we have inclusion of quartz. And this is also a very nice shear sense indicator. So this is the dextral kind. Okay, so no, this is the, it is the sign convention, it is sinistral. The grain is rotating sinistrally while the deformation is going dextrally. Okay, so the all over the flow over the rock is dextral, but the grain is rotating in its opposite direction, which is sinistral. Okay, so this is the rigid body example of grain rotation, although it is not a rigid body rotation. So we can, it is also possible that if a very competent grain is showing rigid body rotation during deformation of rock, so this is a possible case. Then we come to rigid body translation. If you put an object which initially at some point and place it to another place, okay, another position, this kind of deformation is known as translation. In the translation kind of deformation, there is no change in the volume, there is no change in the shape, and there is no rotation. It is simply translation of a particle from one place to another place. And we can show the displacement field like this, and the particle, the path of the particle is straight. These are not making any curve, circular path, because it is, because there is no rotation involved here. Okay, so it is a simple translation, and this translation is not basically seen by a very large size grain that we can easily observe, but yes, this rigid body translation is also possible in the rock, and although not very common. Then we come to shape distortion, or simply distortion, or shear, we can say. It is at the, as we can see from the flowchart diagram, that distortion or the shape distortion or strain accumulation, this kind of deformation, okay, can be subclassified into pure shear and the simple shear. So while discussing the distortion, shape distortion, at first I am going to talk about the simple shear. Look at this figure. Okay, A and B. Suppose you have a deck of card and you put your hand like this and slide it, so the deck of card will result to be deformed in this manner. Okay, similarly there is another experiment. This is a plate which is lying over oil. Okay, and you are making a force, so the displacement would be like this kind of deformation result in the distortion of the shape of the body. So at first this deck might be rectangular in this deck of card must be rectangular in shape, but when you slide it and deform it, it will become rhombus in shape, parallelogram, rhombus in shape. Okay, now this is a simple representation. This was this square. Okay, and in this square you can see a inscribed circle. Okay, in the light shaded region you can see a square, and within this square you have a circle. And when you slide this, you make a when you apply a force like this parallel to this x-axis here, okay, like this, so the body will deform in this manner. Okay, elongated to these two diagonal point, and shortening will be in these 2 points. Okay, these 2 point will tends to shorter. Okay, the displacement field would be like this, somewhat like this, and you can clearly see, if you make this, you can see the field where it is deformed. So this is the maximum strain accumulation axis, where the maximum extension is taking place along this, from this point to this point. If you connect this point, a diagonal, this diagonal will be the maximum extension showing the, this is the path of the particle. And here we can see the regime. Okay, so in this regime, this we can divide the whole circle. So circle was present in an undeformed body. Okay, so this is the circle representing the undeformed body. Now as the strain is accumulating, the body is being deformed, the circle is becoming elliptical. That means ellipse shape. Okay, so it is becoming more elliptical, more and more elliptical, and becoming uh, ellipse shape. Okay, so this white regime is showing the extension, or this stretching regime, while this creamy layer is showing the shortening regime, where the lines, material lines, are going to be shortened. Okay, so if you put a material line in this creamy layer region, and after deformation you can find that that material line developed fold. Okay, because the shortening is taking place. While if you make a if you orient a material line in this white regime, so after deformation what you can possibly get is boudinage structure. Okay, so here it is mentioned at is ISA1, that means instantaneous stretching axis 1. So this is the axis of maximum extension. Okay, and in this creamy layer we have this ISA3, this purple one, this one, ISA3 axis, and this axis is instantaneous shortening axis. So it is the axis where maximum shortening is taking place. As you can see, as the gradually this circle is becoming deformed because of the applying stress over it. It is gaining a strain. Moreover, it is rotating, so it is an uh, non-coaxial non-coaxial deformation, because the axes are rotating. As you can see here, the position of these axes are rotating. These are trying to align along this line 1. So you can see this point, this line 1, this is the line 1, and force is being applied in this parallel to this. It might be, it must be dextral. Okay, it is try to orient it dextrally. We are making shearing it, and that force line is parallel to this axis 1. So all the material line are trying to orient themselves along this one, along the try to orient themselves parallel to this line 1. Okay, so initially this line, this 4, this, look at this line 4, it is at this position perpendicular to the line 1. But as the strain is being accumulating because of the increasing stress in the body, it is this line 4 is try to orient itself parallel to the line 1. So this is uh, highly deformed ellipse here, and you can see here the axis 4, the green color, is being rotated. So this is an example of non-coaxial deformation. And in this what is non-coaxial deformation? Non-coaxial deformation is a kind of deformation in which the axis, or the lines that are storing strain in itself, they are actually rotating. So here the axis, the strain gaining axis are rotating. That means it is a non-coaxial deformation. Okay, so 1 is the only line where there is no deformation. Okay, as you can see here that the length of the 1 is not changing, length of the line 1 is not changing. Moreover, the the line 1 is also not rotating, so it has the only line in the simple shear, this one line, that is the line which is parallel to the vector of force being applied to this body. So this line is not deforming, it is not showing any deformation, it is not showing any strain. Moreover, all other lines are try to orient themselves parallel to this line 1. Okay. After simple shear, the another kind of shape distortion is pure shear. Look at this golf ball. In this condition, at this stage, this golf ball is perfectly spherical in shape. After this is 230 microsecond. After 290 microsecond, it just hit the surface. Okay, as soon as this ball hit the surface, you can see it is no more be maintain its spherical shape. It is deforming itself. Okay, and it's 410 microsecond, it is becoming more and more elliptical. 470 microsecond, it is further more elliptical. Okay, and again it is try to rebound. Okay, and during rebound it is again try to restore its original shape. Okay, which is spherical. So this shape, this condition is uh, is matching with this 410 microsecond. Okay, this 530 microsecond is somewhat like 410 microsecond. Okay, so the maximum deformation is at this stage, and slowly it is recovering, and again it becomes spherical. Okay, so it is a elastic body, this golf ball behaving elastically, deformed, and then again regain its shape. Okay, but when it was deformed, you can see it has it from spherical to it becomes an ellipsoid. Okay, so but in two dimension you can it is looking like a circle which has become ellipse. Okay, similarly, when this is your initially your body is like this square, and this square is inscribed in this square you have inscribed circle, and you apply a force perpendicular to it. Okay, that is parallel to this line 1. Okay, this is your maximum principal stress axis. You are making applying a force parallel to axis 1, and you are then there will be a deformation. Okay, so this body will no longer be a square, rather it will become a rectangle, and this inscribed circle will become ellipse in shape. Okay, and this is extending in the direction of the maximum extension, maximum strain will be in the direction of minimum stress. Okay, and if you look at the flow direction, okay, displacement field, these lines would be like this, and if you look at the path of the points, they will make a curved path like this. Okay, although you can see here that if you suppose if you have this line 1. Okay, so if you have a material line parallel to the line 1, after deformation they have to be shortened. Okay, so if initially I have a line which have is starting from this point to this point, after deformation this had to be limited from this point to this point. Okay, so the shortening will be taking place in this regime, while the extension in this regime, and this can be shown with the help of this diagram here. Okay, so this blue color is indicating the regime of shortening, while the white field is showing the regime of extension. Okay, and the maximum shortening will be parallel to this axis 1. Okay, so this is the axis of maximum shortening. So here we are getting fold, and as we have material line which is as the material line going far away, orienting far away from this axis, there will be less and less and less and lesser accumulation of strain in them, and they will develop a less intense fold. Okay, similarly this x axis, okay, you can see here x axis, here's the maximum extension is taking place. So maximum shortening in this direction, okay, parallel to the 1, maximum shortening, while the maximum extension is just perpendicular to it, and this is forming the Boudinage structure, as you can see here that, okay. So so as it is moving from the maximum extension towards the maximum shortening, so the intensity of the extension will gradually decrease, and these diagonal points where these two regimes are meeting. At this point, these material line, they will neither show any shortening nor show any extension, because it is the boundary of the regime of the shortening and the extension. So these material line will neither show any shortening nor show any extension. So these can be called as axis of no finite change. Okay, moreover, if you have an have an material line which is parallel to this axis 1, okay, so it will not rotate in this pure shear. Okay, they will remain in their original position, they will not rotate. Similarly, if you have this axis, this x-axis, before deformation and after deformation, they will not rotate. Okay, so this kind of deformation is called as coaxial deformation. Okay, so in the coaxial deformation, there will be no orientation or rotation of this axis. And this is the diagram where we can see the strain accumulation. So ISA 3, okay, ISA 3, it is indicating, it is parallel to the axis 4, the green one. Okay, so ISA 3 means the instantaneous shortening axis. Okay, and it is the maximum shortening axis. Okay, and this is ISA 1, instantaneous stretching axis, the maximum stretching axis. The creamy one is showing the regime of shortening, while this white one is showing the regime of extension. So whatever the material line which is falling in this creamy region will deform to give fold, while the material line in this white region will deform, after deformation will yield Boudinage. Although the maximum intensity of the fold will be in the material line which are parallel to the instantaneous shortening axis ISA 3, that is parallel to the green one for line 4. Okay, while the maximum extension, the maximum extension which is taking place parallel to the line 1, ISA 1, instantaneous stretching axis 1. Okay, so they will form the most intensity of the Boudinage, the most intense Boudinage will be parallel to the line 1. So here we can see, as the strain is being accumulated, there will be no rotation of these line 4 and 1. Okay, as you can see, there is no rotation of the line 4 and 1, they will remain at their same place. Okay, moreover, there is no rotation of the ellipse also, you can see. So this is an example of coaxial deformation. And at last, let us come to the last kind of deformation that we may encounter, is change in the volume. Here we have a sauropod dinosaur. These both look identical, but one is very large in shape, another is very small in size. Okay, what is the basic difference between these two animals? There is only one difference, that is their size and volume. If I made this big dinosaur and shrink it to this of this dimension, okay, so there will be no distortion with the shape, because there is no distortion of the face of the dinosaur, neither it has any deformation. Its neck, body, tail, no deformation in this region. Okay, so there is no deformation in the shape, so we cannot call it the distortion of shape. Moreover, it is no rotation, no translation is taking place. So the only deformation is change in the volume. So just volume is being changed. Okay, because of the change in the dimension. Okay, so its length, width, height is being changed, and change in this dimension equally in equal proportion. Okay, so when change in the dimension in the equal proportion is taking place, so the change in the volume take place. And the best example is in the hydrostatic pressure. So hydrostatic pressure is a pressure where when you immerse body in deep under the water, what happens, that body got reduced in volume. There will be no reduction in the shape, no reduction there will be no translation or rotation. Rather, there will be, the body got shrink. So only only change in the dimension or change in the volume will take place. Okay, so the shape will be remain same, but the body becomes less in volume. It got shrink. Okay, so we can observe this in hydrostatic pressure, while the rocks, they do observe such deformation in lithostatic pressure. So in the lithostatic pressure, where all the principal stress axes are of same, that means sigma 1, sigma 2, sigma 3 all are equal. So uh, in such condition, there will be only change in the volume take place, no other deformation is taking place. So such deformation is called as change in volume.